we're going to start with a consecutive integers problem. So consecutive integers problems are basically requiring you to identify, know what an integer is. And this is one reason I really hate that we don't do real numbers first, but we need to know what an integer is, and an integer is any positive or negative whole number, okay? So right now we're not dealing with fractions or decimals, everything's gonna be a whole number. So I want 3 consecutive integers whose sum is 300, okay? So we do not know what the integers are, but we know we have integer 1, integer 2, integer 3, okay? And I'm going to draw a number line to help help everybody understand this. So integer 1, we have no clue what it is. So it is x, okay? Integer 2 is, we still don't know what that is. We just know it's whatever x is plus 1 more, okay? It's plus 1 more. So this is really x plus 1. So integer 2 is x plus 1. And then integer 3, we know it's whatever x was plus 1 and then plus another 1. So we're going to let integer 3 be x plus 2. So this represents our 3 integers. We have our first integer is x, our second is 1 more than x, our third is 2 more than x. And we know their sum is 300. So we know sum in math, we translate that to addition, and we translate to equals. So we know that x plus 1 plus x plus 2 equals 300. So we're going to solve this by combining like terms. I have 3x, and I have 1, and I have 2. So plus 3 equals 300. I'm going to subtract 3 from each side. I get 3x equals 297. I'm going to divide each side by 3, and x goes into 297 99 times. So my first integer is 99. My second integer is going to be 99 plus 1, which is 100. And my third integer is going to be 99 plus 2, which is 101. So they're consecutive, they're in a row, and that is how we're going to do these, okay? Let me just make one note about if it says even or odd. So if it says an even or odd, so I'm going to do a little thought bubble over here. If it says even or odd integers, here's the thing you have to understand about even or odd integers, okay? So even or odd numbers are every other number, okay? So let's say this had the same type of problem with even integers, so 3 consecutive even integers. So this is my first even number, and we know even numbers increase by 2. So my second even integer would be x plus 2. So it's 2 more, okay? My third even number would be x plus 4, because it's 1, 2, 3, 4 more, and so forth. So this is true for evens and for odd numbers. So even though it's an odd number, we're still going to do plus 2 and plus 4, because each time we're skipping the other number in the middle. So this is just a thought bubble for when you have even or odd problems, because you'll see them. Those are usually x, x plus 2, x plus 4. So that takes us past consecutive integers, and that brings us into uniform motion problems. And uniform motion problems are always those problems that you'll see on TV where people like the train, whatever, goes one way or the other. But they're not that bad. I promise you they're not that bad, especially if you guys make a table, okay? So whenever I do these problems, I always tell students, you're gonna make a table to organize your information, and then from there, it's pretty straightforward. Okay, so I'm going to make this table just like that. So we're going to have 3 rows and 4 columns. And the thing to remember about this is that this is all distance, rate, and time problems. So all of these are going to have to do with distance equals rate times time. Okay, they're all DRT problems. So let's look at the important information here. The important information says that a train, the right color. A train leaves the train station at 1 p.m. Okay, a train leaves the train station at 1 p.m. It travels at an average rate of 60 miles per hour. That's important. A high-speed train, so high speed makes us think it's going to be faster, leaves the same station an hour later. It travels at an average rate of 96 miles per hour. The second train follows the same route as the first train on a track parallel to the first. Okay, so that's important to remember. The tracks are parallel. In how many hours will the second train catch up to the first? So what it's asking us to find here is it's asking us to find time, how many hours. So I always draw a picture when I'm doing these, okay? I have my train station, all right, and I have train one. So train one is chugging along, okay? And then the high speed train comes along and it's chugging along much faster. So it gets to the same point, it's gonna catch up with train one. So train two is gonna catch up with train one. So what we wanna do is basically here, the distance is the same. They're in the same direction. Our distance is gonna be the same. So that's gonna play a factor here. So we're gonna make our table with train one and train two. And we're gonna do distance equals rate times time. So we're gonna fill in what we know. We know for sure that train one has a rate of 60 miles per hour. We know that train two has a rate of 96 miles per hour. Some things we don't know is we don't know either of their distance and we don't know either of their time, okay? We know that train one is our first time at 1 p.m., okay? And our second train left an hour later. So our second train is the same time as the first train minus an hour because it's been traveling for an hour less. So what we're gonna do is we're gonna write two equations here. So for train one, we have the equation distance equals 60t. And train two, I have distance equals 96 times t minus 1. And we're going to go ahead and distribute that and get 96t minus 96, okay? Now, you're like, how do I solve this? There's two variables here. Oh God, it's a literal equation. It's not a literal equation actually, okay? It's not a literal equation. What this equation is we're going to take what we know and we're going to put these together to solve this. We know their distances are the same. We know that they went the same distance because they met up. So we can say that distance equals distance. So if I know that distance equals distance, and this one is 60, and this one has a distance of 96t minus 96, I can say 60t equals 96t minus 96. So when I do this, I'm going to solve this for t. This is one of the few times I'm not going to move the smaller variable. Because I don't want to leave the left side empty, so I'm going to subtract 96t. That cancels. I get negative 36t equals negative 96. I'm going to divide each side by negative 36. And negative is a positive, and we want it to be positive because we can't have negative time. So 96 divided by 36, I don't think that goes in evenly. It does not. We get 2 and 6 repeating. So what we basically get is 2 and 2/3. 2 and 2/3, okay? Because this is one of those few ones we're going to leave it as a fraction because we're talking about time. So the time for our first train was traveling 2 and 2/3 of an hour. Our second train was traveling an hour less than that. So we're going to do 2 and 2/3 minus 1, which is 1 and 2/3 of an hour. So we have both of their times. So that train 2 caught up with train 1 after an hour and 1 and 2/3 hour, which what is 1 and 2/3 hour? Come up here because I'm running out of space. 2/3 of an hour is 60 minutes, okay? What is 2/3 of 60 minutes? So basically I just do 2/3 times 60. It's gonna give me, I'm gonna reduce this, get 1, and I get 20, get 40 minutes. So my first train was traveling for 2 hours and 40 minutes. And my second train was traveling for 1 hour and 40 minutes, okay? So this is same direction travel, the same direction where the distances are gonna be the same. Okay, this is our first type of uniform motion problem. Our second kind of uniform motion problem is round trip travel. Round trip travel. So what that's going to be, and I'm going to see if I could just do this because I really don't want to, oh, it erases my table. Pooh. Okay, round trip travel, if you think about it, is we're going to go somewhere and we're going to come back. We're going to go somewhere and we're going to come back. So the whole trip. We take the whole trip into consideration. We're still using distance equals rate times time. That has not changed here, okay? So we're still using D equals R times T, okay? Rate times time. So this one, Poppy drives into the city to buy a software program at a computer store. Because of traffic conditions, she averages only 15 miles per hour. Must be some bad traffic. On her drive home, she averages 35 miles per hour. If the total time is 2 hours, how long does it take her to drive to the computer store? Okay, so I always like to draw a picture. This is her trip to the computer store, okay? And this is her trip home from the computer store. What do you guys notice about the distances here? What do you notice about the distances? If you notice they're the same, that's exactly right. Our distances are going to be the same again. We're both going to, we don't know the distance, but we know they went the same distance. So we have to the store and home from the store, okay? All right, home from store. So to the store and home from store. So we know the rate going there was 15 miles. We know the rate going home was 35 miles. The tricky thing here is the time, the total time, okay? Now we know the total time took 2 hours, okay? So this gets a little tricky. We know going there, we don't know what it was, but we know T represents the time going there, okay? So T for the time coming home is gonna be 2 minus T. And here's why that is. It was 2 hours total, and if we take away the trip there, that would give us the trip home. So T was our trip there, and 2 minus T would give us the time home. Because what's remaining after we take away the time there is going to be what it took to get home. So my two equations are distance equals 15T and distance equals 35 times 2 minus T, which we could say is distance equals 70 minus 35T. And we know here that the distance were the same because she went the same place. She went somewhere and came back, so she traveled the same distance. So since our distances are equal, since D equals D, I can substitute 15T in, and I can substitute 70 minus 35T in. Okay, I'm going to solve this for T by adding 35T to both sides. This cancels, and I get 50T equals 70. I'm going to divide each side by 50. And I get T equals 7/5, which is T equals 1 2/5 of an hour. 1 2/5 of an hour. So come on, let's come up over here and see what that actually is in real time. So 1 2/5 of an hour, we know an hour is 60 minutes. So 2/5 of 60 minutes is 2/5 times 60. So we're going to cross through, so that goes in there once, that goes in there 12 times. We have 24 minutes. So 1 2/5 of an hour is 1 hour and 24 minutes. Let me do that in different color. Oops, I didn't mean to do that. Let's just do this. Let's do it in green. So we know that the drive there took 1 hour and 24 minutes. That was a long drive because she was going really slow. All right. The drive home is going to be 2 minus that 1 hour and 1 2/5 hour, or 1 hour and 24 minutes. You can do it either way. You can leave it as a fraction or change it to the minutes. So I'm going to leave it as a fraction for this part. So 2 minus 1 2/5 is just 3/5. So 3/5 of an hour is going to be what in minutes? Again, we just do 3/5 times 60 is going to give me 36. So it took her 36 minutes to get home. So it took her 1 hour and 24 minutes to get there because of traffic and 36 minutes to get home. So that tells us how long it took to drive to the computer store, and we finished it up by saying how much it took her to drive back. So this is round trip travel. Again, the distances are still the same. The next kind of problem we're going to see for uniform motion is opposite direction travel. Opposite direction travel. So this is the first one we're going to see where our distance is not going to be equal, okay? So let's work this out. So I'm making my little table. We're still doing just anytime it's uniform motion, we're doing distance equals rate times time. And you've probably seen that. I know you've seen that in 8th grade science, because that is, I used to be really good friends with the 8th grade science teacher at my old school, and I know you guys use that. So in this one, Pippa and Dewey leave their home traveling in opposite directions. That's important, on a straight road. Dewey drives 15 miles per hour faster than Pippa. After 3 hours, they are 225 miles apart. Find both of their rates. So this looks a little bit different too, because we're finding the rates, whereas before we were usually finding time. So let's plug in what we know. We have Dewey and we have Pippa. So let's draw a picture. So they start at home. This is their home. And Dewey is driving one way. And he's driving faster than Pippa. Okay? Pippa's driving the other way, slower than Dewey. And they're on a straight road. So let's see what we have. Let's go on what we know. We know both of their times. We know both of their times. They both were driving 3 hours. They left at the same time, and they both drove 3 hours. So that's a little bit different. Usually we don't know time. All right, we know that Dewey drives 15 miles per hour faster than Pippa. We know that he drives 15 miles per hour faster than Pippa. So we don't know Pippa's rate, but we know that Dewey's rate is Pippa's plus 15, okay? We know they're 225 miles apart. That's going to come into play in a second. We don't know their individual distance, so we're going to put D in for both of those. So again, you guys are like, okay, now there's two variables. I can't solve that. But yes, you can. So what's going to happen is we have that Pippa's distance is 3R. And we have that Dewey's distance is 3 times R plus 15, or in that case, 3R plus 45. Okay? Now, here's what we know. We know that their total distance altogether was 225. That means that Pippa's distance plus Dewey's distance equals 225. So we know that distance plus distance equals 225. So what we can do here is we can plug in what we know. We know that Pippa's distance is 3R. We know that Dewey's distance is 3R plus 45. So we're going to plug these both in, and we know they equal 225. So we combine like terms. I get 6R plus 45 equals 225. We're going to subtract 45 from each side. We get 6R equals, what's going to be 180. Yeah, that's right. And we're going to divide each side by 6. We get that the rate is 30 miles per hour. Okay, now whose rate is that? That is Pippa's rate. Pippa is going 30 miles per hour. Dewey is going 30 miles per hour plus 15 faster than that. So Dewey, the little speed demon, is 45 miles per hour. Okay, so this one, opposite direction travel, you need to realize that their distances add up. So we're going to add these equaling their total ground covered. Okay, so that's our uniform motion problems, and kind of a rundown on that. Just remember that this table is your best friend. This table is like the best thing you can do for these problems. Like, they're so easy once you master that table, okay? All right, I want to do 2 quick inequality word problems. The first one is you rent a car and are offered 2 payment options. And let me just start by saying this is a very real problem. I have actually had a situation just like this when I went to Alaska and I rented a car. I could rent from one company that was cheaper, but after a certain amount of miles, I had to pay like $1 a mile, which was crazy. Or I could rent from another company. It was more expensive, but I had unlimited miles. Okay, so this kind of compares those two things. All right, so you rent a car for 2 different payment options. So right there, I know I'm gonna have option 1 and option 2. Okay, you can pay $25 a day plus 15 cents a mile. So we see plus, we automatically know this addition. So option 1, we know that our cost is $25 a day plus 15 cents for every mile. Okay, or you can pay $10 a day plus 40 cents for every mile. So our other option is going to cost us $40 plus, or $10, not 40, $10 plus 40 cents per mile. Okay. So this is what we're going to look at here. The first option is more expensive, but you pay less per mile. The second option is cheaper, but you pay more per mile. So for what amount of daily miles will option A be a cheaper plan? So we want to know, when will option A, so let me change these, A and B, when will A be cheaper than B? So if it's cheaper, we want to know when it's going to be less than B. We want to know not what it's equal to, but less than B. So what we have to realize here is that option A is the cost equals 25 cents plus 15 cents a mile. The thing is, we don't know how many miles we're going. So we're going to put M in to represent these unknown miles, because we could maybe drive 100 miles, we could maybe drive 10 miles, depends. So option A is going to be 25 plus 15, or 1500th M, is less than option B, which we're going to do the same thing. We still don't know what miles are for option B, so we're just going to put in M, which is 10 plus 4/10 M. So now we're going to solve this for M. So I am going to subtract 1/1500th M from each side. Okay, and I'm doing that because this is really 40. So we get 25 is less than 10 plus, basically we do 40 minus 15. 40 minus 15 is 25, and we just make it a decimal, 2500th M. We subtract 10 from each side. And so I get, I'm going to come over here and work, I get 15 is less than 2500th M. So we're going to divide each side by 2500ths. One thing to notice here is that I am not dividing by negative, so I do not need to worry about switching my sign. So I do 15 divided by 2500ths, I get 60. I get 60 is less than M. Now, this looks weird. M is on the right side. That bothers a lot of us. So if I flip it around, that is fine. I just need to make sure the big open mouth is facing M here. So the big open mouth has to face M here. I always read these starting with the variable. I read them wherever the variable is. So this one I would read from right to left. M is greater than 60. I just need to make sure this one reads M is greater than 60. Oh, look, it does. Awesome. Okay, so again, I always read these wherever the variable is. I start the variable and I read, sometimes I read left to right, sometimes I read right to left. So the M is greater than 60. So what does this mean? What does this mean? That means you have to drive more than 60 miles for option A to be cheaper. Okay, for option A to be cheaper. Okay, so if I plugged in 60 here, if I plugged in 60 and worked this out, all right, if I said 25 plus 1500 times 60, that is going to give me $34. And then over here, if I do 10 plus 40, 4/10 times 60, that's also gonna give me $34. So if we do 60 miles exactly, if we do 60 miles exactly, they cost the same. Okay, they cost the same. But I want to know, when is A going to be cheaper? Well, if I do more than 60, A will be cheaper. So if I do the same thing, except for this time, I plug in 61. I plug in 61. Let's see what happens. Okay. So 1500ths times 61 plus 25 is going to be $34.15. And then I'm going to do the same thing, 4/10 times 61 plus $10. It's going to be $34.40. So it's not that much cheaper, but it is cheaper. So 60, anything greater than 60, option A will be cheaper. But what that means too is that anything less than 60, option B will be cheaper. So option B is cheaper if you're driving less mileage. So like if you needed to rent a car for around town, maybe you would consider option B. If you needed to rent a car to say drive across the country, we're definitely gonna be looking at option A because we're gonna be driving more than 60 miles, okay? So M is greater than 60. That means we have to drive more than 60 miles for option A to be cheaper. The last one I'm gonna do is this elevator problem. I did one like this for a warm up in class, but I just wanted to build on it and make sure everyone's comfortable with it. So a small elevator has a capacity of 1,000 pounds before the cable holding it in place snaps. 6 people get on the elevator. So right there, what that means is that every elevator is held by a cable. If too much weight gets in it, it will snap and break, okay? So we want our elevator, the weight in our elevator, to be what? Do we want it to be more than 1,000 pounds, greater than or equal to 1,000 pounds, less than or equal to 1,000 pounds? So it has a weight capacity of 1,000 pounds. So I want the weight to be less than, it can be equal to, but I prefer not to be, honestly, but less than or equal to 1,000 pounds, okay? So it can be 1,000 pounds, it can be less than 1,000 pounds. If we end up with a weight that is greater than 1,000 pounds, we're all gonna die, okay? So the cable holding in place will snap if this goes over. We have 6 people in the elevator. 5 of their weights are as follows: 146, 180, 130, 262, and 135. Write an inequality which describes the amount the 6th person can weigh without snapping the cable. So this is basically an average problem, okay? Or actually, this isn't even an average problem. We don't have to do an average. We just have to add these up and hope that they do not go greater than 1,000. So what we have is weight 1 of person 1, weight 2 of person 2, weight 3, weight 4, weight 5, and then the 6th weight, and we want all these weights to be less than or equal to 1,000. So we're going to plug in the weights we have. So 146 plus 180 plus 130 plus 262 plus 135, and we do not know our last weight. This one is unknown, so we're going to put in a W because it's weight. We don't know it, and it's less than or equal to 1,000. It's less than or equal to 1,000. So to solve this, we're going to add all these up. So I'm going to get my calculator, and I'm going to type in 146 plus 180 plus 130 plus 262 plus 135. So we get 853 pounds are in this elevator so far. So 853 pounds plus this last person's weight has to equal to, or less than or equal to 1,000. So to find out what that last person can weigh, I'm going to subtract 853 from both sides. So I do this, I'm going to get 1,000 minus 853. And I get that the weight of our last person has to be less than or equal to 47 pounds. So what this means is the last person can weigh 147 pounds, they can weigh 146 pounds, they can weigh 100 pounds. Preferably it's going to be a small child, but if they weigh more than 147 pounds, that elevator cable is going to stop and everyone's going to die, okay? That sounds terrible. So what this means is that the 6th person, and I don't know what my pen's doing. I used to make my students always write their answers and complete sentences for these because it helps you understand what you're doing. So the 6th person must weigh 147 pounds or less. They have to weigh 147 pounds or less for the elevator to not break. Okay? So that is the basis of what we need to know with our word problems. I went over the major types: consecutive integers, consecutive even and odd integers, all three types of uniform motion, and two different types of inequality word problems. All of these are good to go over and review. We will definitely review these more towards our EOC, but I want y'all to be comfortable with these and know how to navigate around these. Okay? Have a good day.